Hello everybody. Let us talk about measurements in quantum mechanics, and we will also look into postulate 4. To measure an observable A, consider the eigenvalue equation of the operator A, which is given by A cat un equal to lambda n cat un. So what you see here are two terms, one is operator and the other is observable. An operator is an observable when you can measure the operator. So since we are doing the measurements, so therefore particularly I'm talking about the observable A. Lambda n are the eigenvalues of this operator A, because the observable A or the operator A basically is a matrix only, so it will have its eigenvalues. So let us say lambda n are the eigenvalues of this observable A. So we are assuming that it has got n eigenvalues, lambda 1, lambda 2 up to lambda n, and corresponding to these eigenvalues, this operator, this observable will have n eigenstates. Corresponding to lambda 1, it will have cat u1, lambda 2 it will have cat u2, and so on. Now let us consider an arbitrary quantum state cat psi and is normalized such that the norm of the quantum state is equal to 1, which means the inner product of psi with itself is 1. Now according to Bond's rule, the probability of getting a particular measurement outcome, which will be one of the eigenvalues of this operator, this observable A, that means when you try to measure observable A, you will get one of the eigenvalues as its outcome, and the quantum state will change from psi to corresponding eigenstate, and the probability of getting a particular eigenvalue lambda n is given by magnitude square of the projection of psi onto the eigenstate un, or the inner product of un and psi take its magnitude squared. That will be the probability of getting that particular eigenvalue as the measurement outcome. But definitely when you try to measure property of the quantum system, so you will get one of the eigenvalues of the observable, and in our case we are taking an observable A. So therefore probability of the quantum state collapse to lambda n eigenvalue. So there will be a collapse of the quantum state from the quantum superposition to an eigenstate corresponding to this eigenvalue lambda n. So this is given by the magnitude square of the projection of psi onto the corresponding eigenstate, which is basically un, to the un, because un is related to lambda n. So therefore the collapse will be the probability of getting lambda n as the output is given by the projection of psi onto the corresponding eigenstate, which is eigenstate corresponding to that particular eigenvalue, and you take its magnitude squared, so that will be the final probability. So corresponding to all the eigenvalues of A, we will have corresponding eigenstates and the probability outcomes, probability of the eigenvalues, probability of all the eigenvalues that we can get as a measurement outcome. So it will be given by Bond's rule. Like for example, if you have the eigenvalue lambda 1, the eigenstate will be cat u1, and the probability of getting lambda n is given by the magnitude squared of the projection of psi onto the eigenstate u1, and so on. Now to carry forward the case, let us imagine the quantum system with multiple copies. Let us say we have capital N copies of the quantum state, rather than having only one copy, and we measure all the copies, we measure the quantum state for all the copies. Now let us say in the first case, when we measure the quantum state, we get an eigenvalue of lambda 10. In the next case, we may get lambda 1, lambda 99 and lambda 10. And in all the capital N measurements, we will get some eigenvalue as the measurement outcome. And some measurement outcomes will repeat. So therefore, lambda 10 can come 2 times, 3 times, 4 times. Similarly, lambda 1 can come 2, 3, 4, 5 times and so on. Let us say for a particular lambda n, and we assume that, let us say, it appears as the measurement outcome Pn times. So from the central limit theorem, we can say that as capital N approaches infinity, this ratio of the number of times lambda n comes as the measurement outcome divided by the total number of measurements is the experimental probability of getting lambda n. And we also know the probability of getting lambda n as the measurement outcome. We can obtain it from the Born's rule also. Now this experimental probability will approach to Born's rule as capital N approaches infinity. In so therefore quantum mechanics tells us exact rate at which we will get a particular lambda n when capital N approaches infinity. Now let us say that the quantum state psi, we can express this quantum state psi as a summation of the basis states or the eigenstates and their coefficient, the summation of the eigenstates and their coefficients as a linear combination of the basis states. So that we can express a quantum state as. So ket un are the eigenstates, cn's are the expansion coefficients or the representations of ket psi in the ket u basis given by the projection of psi onto the u basis. But we know that Cn is given by, the coefficients are given by the inner product of un with psi. So therefore, we can say that the probability lambda n is given by mod square of that coefficient. So this is using the Born's rule. Now a special case comes when the quantum state is one of the eigenstates. Let's say ket psi is equal to ket um, that means one of the eigenstates. In that case, the coefficient value will be equal to 1 and the probability of getting that particular eigenvalue corresponding to Cm is 1. Let us now, based on this measurement results, which are basically the outcomes of the measurement, which are the eigenvalues, one of the eigenvalues we will get as a measurement outcome, and what will be the state of the quantum system after measurement is the state is one of the eigenstates corresponding to the eigenvalue that we have obtained as a measurement outcome when we measure that observable. Now postulate 4 states that when we perform a measurement on a quantum system, the possible outcomes correspond to the eigenvalues of the Hermitian operator associated with that measurement. Now, as I have just described, that the measurement outcomes will be certainly the eigenvalues, but the operator or the observable has to be Hermitian operator. Why it is so? Because the Hermitian operators will have eigenvalues which are real numbers. So Hermitian operators will have real eigenvalues, and it is a condition for measurement, because when we measure we must get a real number as the outcome. So therefore the operator for which, or the observable for which we are trying to measure the characteristic, it has to be Hermitian, because the eigenvalues are Hermitian, and we know that we have to get one of the eigenvalues as the outcome so therefore we should get a real number as the measurement outcome. So therefore it's a condition for the operator which we are trying to measure. Now in postulate 4, we are making the following assumptions: that the quantum state psi is normalized, meaning by the inner product of ket psi with itself is 1. Eigenvalues form a non-degenerate spectrum. So what is a non-degenerate spectrum? One eigenvalue can have more than one eigenstates. If it is so, it is a case of degenerate spectrum. That means if one eigenvalue has got more than one eigenstates, so this type of spectrum will be termed as the degenerate spectrum. But we are assuming in postulate 4 that all the eigenvalues are non-degenerate. That means every distinct eigenvalue will have a distinct eigenstate. Eigenvalues form a distinct spectrum like this. So let us look at this graph. Along the x-axis are the eigenvalues, along the y-axis is the probabilities of each eigenvalue. Lambda 1, let's say, has got likelihood of appearing as the measurement outcome, and this probability is mod c1 square. Lambda 2 is mod c2 square, and so on. So therefore we actually form or get a kind of probability distribution which is basically the eigenvalue, which is basically the probabilities of those eigenvalues which can appear as the measurement outcomes. And the higher the height of the spectral line, higher is the likelihood that this particular eigenvalue will be the measurement outcome. Now let us look at the normalization condition. Let us try to look into the analytics of the normalization condition. And the normalization condition is given by the inner product of psi by itself. So we know that psi can be put as the summation of eigenstates and the multiplication of the coefficients, because in this inner product one term is the ket, the other term is the bra. So if we take the bra of psi, you will get the bra of un and the conjugate of the coefficient. So if you do further, a little bit of further maths, and you take Cm out from here, right, we are taking different index because afterwards we will get a Kronecker delta as the output, and we will try to look into the output when n is equal to m. Let us see that. So you take out the coefficient from here like this, and this will be, what is left will be the inner product of un with the un, and this value is basically the Kronecker delta between n and m, right. So this Kronecker delta is 1 when n is equal to m, otherwise it is equal to 0. So therefore when it will be equal to 1 when n is equal to m. So if you do that, you will basically get the summation of all the probabilities of all the eigenvalues. So therefore, since these are probabilities, so the final probability will be equal to 1. So therefore we can say that the normalization condition is given by, that means the inner product is given by is equal to 1. So therefore it proves that the quantum state is normalized. So if ket psi is normalized, then only the quantum measurement is probabilistic in nature. Of course, if inner product is 1, then only the summation of the probabilities can be 1, and that forms the probabilistic measurement outcome. However, if ket psi is not normalized, so this inner product will not be equal to 1, but it will be equal to certain value n. In that case, we will have to normalize the quantum state. So we will have to normalize. So probability of lambda n has to be normalized like this by dividing it by the norm of the quantum state. Now there is a theorem called spectral decomposition theorem. It states that in quantum computing, non-degenerate eigenvalues, we are particularly talking about the case of non-degenerate eigenvalues, because for the degenerate eigenvalues, we will take a separate case, and I will make a separate video for that. So in quantum computing, non-degenerate eigenvalues and their projection operators play a significant role in understanding measurement, quantum observables, and state space spectrum. So let us say we have an observable A with set of eigenvalues as AI and set of eigenstates as ket AI. So spectral decomposition theorem states that this Hermitian operator A, we can express it as the summation of the eigenvalues, the summation of the product of eigenvalues with the projection operators. This is known as the spectral decomposition theorem for a particular observable A. Thank you very much. Thank you.